Everyone, today we're going to talk about properties of logs. This is the second day of our little logarithm unit, and what I want you guys to do is these are going to be our notes for today. So this is what we want to jot down in our notebooks. And what we're going to start with is some basic evaluation things which tie into the assignment I had asked you to do yesterday. Let's go up to the top here. I want you to evaluate log base 5, 5. So let's talk about what that would do. If you guys were to rewrite these, you would set this, let's say, equal to x. So this would become 5 to the x equals 5. Now, what would make that happen? If the exponent is 1. So when you evaluate this, we get a 1. Now let's take a look at this guy. Base is radical 7. I don't know what the exponent is, but it's got to equal radical 7. Well, what would that make? Once again, 1. So what I'm trying to get across to you guys is anytime the base and the number are the same, the answer to the log will always be 1 because that means you're raising the base to the power of 1 to get itself. So let's look at these two now. Log 10. Now, as we discussed yesterday, anytime you don't see a number there, it's the common logarithm. That means you can assume 10. So 10 to the x equals 10. So that would equal 1. And once again, natural log of e, he's going to be one of the most famous ones we see. Again, because that base is e to what? Give us e? Once again, 1. And again, this guy is going to be super famous. He pops up a lot. So anytime we see this, we know it's going to be equal to the number 1. So to sum up, for log base bn, whenever b and n are the same thing, that means the answer to the log is always going to be the number 1. So that's the important part in the first section. Now let's take a look at this next section where it says evaluate. And notice no matter what the base was, I have these all being 1s. And obviously there's going to be a connection there just like above. So here I have 6 to what power would make it 1? And I'm hoping you're thinking, Miss Duffy, we know it's 0. So let's take a look at this next one. Radical 19 to what power would make 1? Again, that would have to be 0. So to sum, if you had to guess what these would, to sum up, to guess what these would have to be, 10 to what power would equal 1? That's 0. And yes, this guy, even with the base e, would also have to be 0. So anytime you see a 1 next to a log, so whenever you have this situation, when n is 1, the answer has to be 0. These both are very important. They pop up all the time in calculus. And then when you see them, you know this is 1, this is 0, you move on. All right, now let's take a look at these next couple. Right? Evaluate this guy. All right, so this one here would mean 2 to what power equals a negative 1? What could we raise 2 to so that the answer would be negative? And I hope you're feeling a little confused because the point is there isn't anything. Let's think about what the exponent graph would look like. Let's say 2 to the x, right? That graph looks like that. If you notice, it always is above the x-axis. We never have negative answers. So this, there's no solution. It can't happen. Okay? There's nothing there. Or you can put the null set even. Doesn't exist. Same deal here. Let's take a look at this. B squared is equal to 9. All right, you're like, well, Miss Duffy, if we do this, technically we get b plus minus 3 for that guy. Something I want to keep in mind. By the definition of exponential functions, the bases can never be negative. So whenever we're dealing with logarithms, we can only have a positive base. And that is because the definition of exponential functions, the bases have to be greater than 0. So only positives for this guy. So in this situation, b would equal 3 only. So what I want to talk about is what we can summarize from this. For a log equation, b has to be greater than 0, and that is because the definition of an exponential function, the base has to be greater than 0. And n, this number here, can never be negative because exponential graphs asymptote. So this guy would also have to be greater than 0. And that's going to be important to keep in mind when we get to solving equations by Thursday or day 4. One final thing in our notes, and then we're going to practice some things, is this bottom part, the 3 log equivalencies. And these 3 things are extremely important even in calculus. Keep in mind we want that logs equals exponents. And that's the key to understanding these guys. If logs give us exponents, these equivalencies occur because, let's say, you're multiplying 2 things with the same base. What would you do to the exponents? You would add them. And that's what this is saying. If you're multiplying 2 logs, and it's got the same base, that means you're adding their individual exponents together. So in the land of the logs, multiplication can be converted into an addition question. Similarly, right, when we did division, what did we do to the exponents? We subtracted them. And that's why here in the land of the logs, anytime you see a division, it can be changed into a subtraction question. And finally, what did we do when we had a power raised to a power? We multiplied them, and that's what's happening here. This would be an exponent being raised to a power, and that means we multiply those values together. So we can use these 3 equivalencies to answer questions or alter things. So these are our notes. And now what I want to do is we're going to practice some things. So let me give you some examples to start with. So here I have 3 different examples or 4 different examples of how we can use our equivalencies to change things. So let's take a look at the first one. We have log a cubed times the 5th root of b. So we want to rewrite that as an equivalent expression. Well, on the other page where I had the notes, I said that multiplication in logs was the same as addition. So the first step I could do here is change this to be log a cubed plus log the 5th root of b. Now, the 5th root of b can be changed. So I'm going to make this log a cubed plus log. This would become b to the 1/5 power. And finally, that third rule in the equivalencies was anytime a log was raised to a power, the exponent can fall down in front and become multiplication. So this would become 3 log a plus 1/5 log b. And that would be the answer to this question. So now let's give this one a try. So we see it's division, so I'm hoping you're thinking, hey, that can change into a subtraction question. So, and the other thing I'm going to do is the radical a, I'm going to make that into a 1/2 power. So to start, this becomes log n a to the 1/2 minus, now there's more than one thing in the denominator, so that means I'm going to put it in parentheses, minus log n b, but notice that's being multiplied to c, so that means I can change that into an addition. One last step, any exponents want to fall down in front, so this guy right here. So this answer will become 1/2 log base NA minus log base NB plus log base NC. If you wanted to do it out where you distribute the minus sign, you can do that as well. I'm happy with that. Again, if you wanted to distribute the minus sign to both of those, that would be fine as well. Now, these two are the other direction. They're in expanded form already. You want to condense them. Now, what I want you to notice, if you go back up to these, look what we have here. When you condense them, it condenses down to one single logarithm. You're not going to write log more than once. So when I see this, I know we're just going to write 1 log base b, just like that. Now, the first thing I notice is the 4 in front. That means that's going to become his exponent. And then the plus sign means I'm multiplying it to this. So this becomes log w to the 4th times y to the 2/5. So that's the first step. Then you want to take your rational exponent and create a radical with it. So this will become log base b w to the 4th. Bottom number is the root, so it's going to be the 5th root of y squared. And that would be the answer to the question. If you want to put a times sign between them, you can do that too. All right, finally this guy, right? That has got to apply to both of these. Right? So this, to me, means I've got log a, that becomes 2/3 minus log b to the 1/3. Subtraction means this is going to become a division question. Now keep in mind, when you condense it, you're only going to write the word log once, or the function log. Log, right? This becomes a to the 2/3 over d to the 1/3. Now if you notice, they're both got the cube on the bottom. That means they're both getting a cube root, so I'm going to change this. They're both going to be inside a cube root. This is going to be a squared, and this is going to be a d. All right, so what I'd love for you guys to do now is here's some for you to practice. So pause the video, try these 6, and then put me back on and let's see how you did. So again, pause it, try these, and then see how you did. Don't just watch me do them, it's better if you practice. Okay, so I'm hoping you pause me. I'm going to work these through now. Let's see how you did. So this guy's division, so it's going to turn into a subtraction question. So this guy becomes log b to the 1/3 minus log c squared. And now any exponents will have to fall in front. This is 1/3 log b minus 2 log c. And that's the final answer. Let's try number 2. A lot going on in number 2. First off, in the numerator here, there's 2 things being multiplied together. So these are going to turn into addition. And then we're going to divide it, so subtract these guys away. So I'm getting log a squared plus log b. Now, if you want to separate what's in the numerator away from what's in the denominator, it's a good habit to get into. So we got that guy. So this becomes now 2 log a plus log b minus 1/3 log c. So this is an acceptable answer, or if you want to put parentheses around the first 2, you could always do that as well. So that's the answer. All right, look at number 3. A lot going on in number 3. So we got log b cubed plus log c to the 1/4. So that's all in the numerator. Minus, now anytime it's division, subtracting, because subtraction, the minus sign has to distribute, you must put things in the denominator in a parenthesis. So this would be log d squared plus log. So this now becomes 3 log b plus 1/4 log c minus this guy. Oops, look what I did. I forgot to put the 2 down in front. Let's fix that. Minus, this 2's got to fall in front. All right, so that's an acceptable answer, or this guy would be an acceptable answer. All right, either one. But it's so important that anytime you're dividing, if there's more than one thing in the denominator, it is in a parenthesis. All right, let's take a look at this guy. Now, this is the opposite direction. It's already expanded. So we want to condense it. Now, when you condense it, it should always go to one singleton log. So I'm going to write the word log once. Right? And this looks like it's going to become a squared times b to the 1/2, which is the square root of b, divided by, because it's a minus sign, the 5th root of c. How'd you do? All right, now let's take a look at this guy. It's getting fancier now. Now, let's take a look at what we have here. So it's division, right? He's got his exponent. Now there's 2 different ways of doing this question. I'm going to do them both ways. One way of doing it was to change this into the natural log of e to the 2x all over e to the x plus 1. All right, next step. Hey, these are the same base, right? So you could subtract the exponents. So that would become 2x minus x minus 1, which would be x minus 1. So this becomes the natural log of e to the x minus 1. Now, if you notice, his base right here would be e. So that means e to what would be the same thing as e to the x minus 1. What would that question mark have to be? That question mark would have to be x minus 1. So that's the answer to the question. Another way of doing it. Another way of doing it. I would have done it this way. Let me get a different color for you guys. I'm going to bring this down. When I see this, I'm going to have it fall in front. So it's 2x, natural log of e. Bring down the minus sign. This also wants to fall in front. X plus 1 times the natural log of e. Now, earlier, we talked about this guy. What is the natural log of e? 1. So he becomes the number 1. So that leaves me now with a 2x here minus x plus 1. And wouldn't you know, that gives me that guy. I would have done it this way. But there's more than one way of doing this that gets you the right answer. All right, and finally, let's take a look at this guy. I'm going to distribute this. So this becomes 2/3 log A plus 2/3 log B, right? Minus, this would be 3 log C plus 12 log D. So I distributed the 3 inside, still got the minus there. So these two are going to get multiplied together. So I'm going to condense this now. I'm going to bring down to a single log. Make sure you guys can see this. So both of these are getting the same thing. So that means both of those are going to look like that. Both of these are getting squared inside a cube root, being divided by c cubed times d to the 12th, right? Which I would take that as an answer. Or if you had a squared, b squared, like that, over this guy, b to the 12th. All right, there you go. How'd you guys do? All right, a couple more things I want to show you and we'll be done for today. Are these ones. A little different way of asking. If n equals b squared times the cube root of a, then what is log n equivalent to? So that means instead of it just being n, I want it to be log n. All right, so here's the deal. If I change n into log n, in order to keep my equation balanced, I've got to do the same thing to this side. So to keep my equation balanced, if I log this side, I have to log this side. So now log n would equal this, and you can keep going with this. This would become 2 log b plus 1/3 log a. So this would be the answer for that guy. So anytime you see that, basically means log both sides. And finally, this is a different way of asking these questions. If log 2 equals a and log 3 equals b, find the following in terms of a and b. All right, first thing I'm giving you is log 6. Log 6. Now, what this question is saying is you only have log 2 and 3 to work with. Well, isn't 6 the same thing as saying 2 times 3? Right, so I changed 6 into 2 times 3. Well, using our log equivalencies, this is equal to log 2 plus log 3. Hey, and what does log 2 equal? Log 2 equals a plus, what does log 3 equal? B. So that would be the answer to number 1. So similarly, we're going to do 18 now. How can you create 18 using 2's and 3's? Well, 18 could be 9 times 2, right? 9 is okay to use because it comes from a 3. And what I would do now is write it as log 3 squared times 2, which then becomes 2 log 3 plus log 2. Now, log 3 is equal to b. So this becomes 2b plus a log 2, which is that. Now, 300. All right, how are we going to handle this? Well, my first gut feeling is 300 is 3 times 100. Now, I know 100 doesn't have to do with 2, but something special can happen. So let's check this out. This becomes log 3 plus log 100. All right, log 3 is definitely b. But this guy is special. What base does a plain log have, or the common log have? That would be 10. So this guy, I'm going to bring over here. This guy is the same thing as saying 10 to what power equals 100. And I'm hoping you're thinking, hey, that's a 2. So that means all of this becomes the number 2. So now this became b, bring down your plus sign, and this thing became a 2. Voila. And there you go, guys. That's properties of logs. And that's a super important topic because we use these now to help us out with equations and things. So this is an important topic we're actually going to sit on for 2 days. What I have for you guys is a practice assignment to see how you do. And I hope you do okay. So I'll be in touch soon. Enjoy.